Hi, Professor. We are Group 1 here to present our project Bayesian model for estimating discriminability and bias in binary decision making using PYMC3. These are our group members. And when coming to next slide, these are our table of contents. And when moving, we are moving to introduction. In here, in this, we use PYMCT to create Bayesian model for qualifying discriminability and bias in binary decision making. And also it assumes logistic functions with single and bias parameters, conducting Bayesian inference through posterior parameter sampling. Output metrics encompass mean true and false positive rates, alongside estimates for discriminability and bias derived from posterior samples. And my friend will continue the theory part.
Coming to theory, discriminability in binary decision making refers to the observer ability to distinguish between two different classes of events. Here, larger d value indicates greater discriminability with lower vocab between distribution. Here, the code represents bias using parameter b, which alters the intent signal in favor of target or noise stimuli. And coming to exploratory data analysis, here code creates kernel density map for posterior samples of discriminability and bias parameters using CPON library. And we have created a plot between density and parameter value, which shows true positive distribution and false positive distribution of the given function. And plot displays probability density function for each parameter value with density on y-axis and parameter value on x-axis. And also map facilitates result comparison of distribution and provides insights into uncertainty and variability in estimation. And the next will be continued by my friend.
In case 2, this code generates a kernel density plots for two sets of data, D samples and B samples, using C1. This allows for visual comparison of the distribution of data for discriminability and bias. Blue graph for discriminability and orange graph for bias. In second part of the code, we are plotting for true positive rate and false positive rate distribution. Visual comparison of the distribution. Blue graph is for true positive rate distribution and orange graph is for false positive rate distribution. Coming to page 2, visual comparison of the distribution density plots for the discriminability and bias distribution in the first part of the code, and in second part of the code we are visualizing the distribution of false positive values and true positive values. We are using Seaborn Matplotlib for plotting. Thank you, and my friend will be continuing from here.
Coming to the results, let's discuss about the case 1 of our classification model. This case gives us a good look how well our model performs. Our model is excellent at spotting true positives. We have measured it with using the true positive rate and we found out to be it's 70%. That's pretty good. And it shows that our model is most accurate most of the time. But still there are some issues while identifying with the false positives. There are cases where it wrongly identifies something positive when it's actually negative. We have measured this with the false positive rate. It is 50%, but it isn't a big deal. Finally, our model distinguished between the different classes. We have measured discriminality, which is measured 0.633 in our model, which is quite good score and tells us that our model is quite accurate overall.
In the case 2, we have the following code. We are first initializing the variables and then defining the model and then setting the prior distribution and then taking likelihood of observed data. And these are the properties of target and noise observations. We are taking the sample from model and tuning it to 1000 and then extracting the posterior samples dB, then printing mean and standard deviation. Under that, we have this TP distribution and FP distribution. And case 3, similar to case 2, we are doing the same thing here again. And then you can see the mean and standard deviation as 0.114 and 0.54, which is the distribution value.
Hereby, I conclude that a Bayesian technique has been used to evaluate the discriminability and bias of binary classifier as well as the true positive rate and false positive rate distributions. After modeling that observed true positive and false positive counts using like a binomial likelihood, YMPC3 was used to sample from the posterior distributions that resulted. It is evident that models bias and discriminability parameters both make use of normal prior distributions. After the posterior distributions of these parameters are acquired by Markov chain Monte Carlo sampling procedure.